2018 question 5. Quartz SiO2, which is silicon dioxide, is harder than dry ice CO2, which is carbon dioxide, because, and you're given the options. So first of hardness. Now, how can we talk about, or how can we relate this question to hardness? So in book 1B, topic 2, Microscopic World 1, you should have learned that to talk about the hardness of any substance, it's because of their structures and their bonding. So here, we'll need to know what type of structure and bonding they have. So let me write down here, quartz, as you should know, they're just a handful of examples of this giant covalent structure, and quartz is one of them. So quartz is having a giant covalent structure, and we know among those molecules they have strong covalent bond. Yep. And that's why you need a large amount of energy to overcome these bonds, and that's why it's hard. It has strong covalent bond. Okay, let me write it better. So how about dry ice? Dry ice, as we know, it's carbon dioxide. Dry ice, carbon dioxide, is it a covalent compound? Or yes, as you can see, carbon is a nonmetal. Oxygen is also a nonmetal. So when two nonmetals are bonded together, it's a covalent compound. And is it one of those handful of just 4 or 5 examples of giant covalent structure? Nope. If it's not, then it's definitely a simple molecular structure. So that's how you know what type of structure it has. So dry ice, it's a simple molecular structure. And what's the attractive forces between the molecules? Yep, it is weak van der Waals force. Now, because it's weak van der Waals force, you just need a very small amount of energy to overcome this force, and that's why the hardness is much less. Okay, so this is the reason why. So now let's look at the options. Option A, the atomic size of silicon is larger than that of carbon. Nope, it's not. It does not answer the question of why it's hard. So this is not true. Option B, a silicon atom has more electrons than a carbon atom. This is also wrong because it's not related to hardness. Option C, quartz has a giant Edwards structure. Oh, now this hits the jackpot. It has a giant Edwards structure. Yep, it makes sense. There's a giant covalent structure. But dry ice consists of discrete molecules. Discrete molecules. Okay, the meaning of discrete is they're individually separate, which is true. Because of this simple molecular structure, it has discrete molecules. You can just imagine it's talking about weak van der Waals force. Just a different way to represent it. So answer is C. But look at option D. Now this is where a lot of you might, fall into the trap. It says the silicon oxygen bond in quartz is strong, which yeah, it makes sense because sir, you wrote it here, right? It's strong covalent bond. But the carbon oxygen bond in dry ice is weak. You're like, oh yes, sir, you wrote here it's weak. So the option should be D as well. Now, this is where you need to be careful. It's not talking about between the molecules. Now, if I could represent it, it's not a correct representation, but I think it's a good way to see it. Now, if let's say I have CO2 here, and I have another CO2 here, okay? Just imagine this is one CO2 molecule, and this is another CO2 molecule. Now, between two of these molecules, the dot that I've drawn here, maybe I'll use a different color. Now this reddish blackish dot here, this is the weak van der Waals force, right? But now the question is asking you, but the carbon oxygen bond in dry ice. So they're talking about the bond that is inside here. So within carbon dioxide, what's the bond there? As we know, within carbon dioxide, it has a covalent bond. So there's no way a covalent bond is weak. It's still strong. Okay, so the same thing over here. When we're talking about the silicon oxygen bond, they're talking about within the silicon oxygen, and that is still covalent bond also. So don't get confused with this. So there's no way this is weak. The bond within carbon oxygen is still a normal covalent bond, which is definitely strong still. So option D is also wrong. The only correct answer is option C.